Hello, I am Abdullah Alhasni, and in this presentation I'll give you my brand new idea for enhancing solar panels performance through water cooling. I'll first give a general view about renewable energy and one of its most popular forms, solar power. Then I'll move on to give a brief explanation about solar cells' operating principle and then go over some of the problems, and finally I will give my solution to the biggest one of them regarding heat. First of all, renewable energy is not only the most abundant but also the cleanest form of energy available. Many projects are now using various forms of it to sustain their energy needs, such as wind energy and hydroelectricity. One of the most effective ways to generate energy is solar power, due to solar energy being constantly available, unlike wind for instance, which is quite unpredictable. There are other reasons to favor solar power besides the sun's consistent presence, such as the abundance of sand in the world that is used to manufacture silicon, which is a main element in photovoltaic cells used in solar panels, just to name a few reasons. I'll now briefly go over the structure of a solar cell. As shown in the following figure, a solar cell generally consists of an electrode, a reflect-proof film, N-type and P-type semiconductors which operate by the photoelectric effect principle, where solar radiation frees bound electrons in the N junction that pass to the electron holes in the P junction by being forced by the electric field formed in the depletion layer, and finally another electrode to conduct the resultant electrons through the circuit to make the current flow. Here is a GIF that demonstrates the principle. Panels are a collection of series and parallel cells that are also usually covered with EVA encapsulants to prevent moisture and pressure from damaging the cells, with finally glass panes being placed on top of them. However, solar panels have many issues, which I'll address some of them right now. Some of the main issues are microcracks, potential induced degradation effect, aka the PID effect, and some electrical issues regarding wiring and soldering, all of which are beyond the scope of this presentation. However, one important problem which brings down the efficiency of solar cells by much is hotspots and overheating due to excessive solar exposure. Hotspots are among the most common issues with solar or photovoltaic systems. They can degrade the function of your solar panels or even render them irreparable. Overheating is another similar issue where panels are not automatically cooled down and are heated up to a temperature where they can't operate as effectively. These two problems can lower the performance and lifespan of the solar panels. Now my proposal is an easy affordable model of water-cooled solar panels. Due to water's high specific heat and density, it's largely used to cool down machines and especially computers. I decided to use water for my project since it could absorb the heat of the panels effectively without heating up much if put in large amounts. A study by Ain Shams Engineering Journal confirms that solar panels show higher efficiency when water-cooled. I now intend to show a simple effective model by which we should be able to make solar panels more operational. Since we don't want water to block sunlight of the panel, my model goes as the following. As you can see in the following figure, a thin water layer can be placed between the solar panel and the EVA protective encapsulants. The thickness of the layer must be chosen specifically such that the electromagnetic absorption of water does not limit the panel's output or block sunlight in any way, something on the order of the EVA encapsulants or sheet's thickness. Of course, such a small amount of water in the small layer wouldn't be enough to absorb the heat of the sun over the entire course of the day, so the second step is connecting the thin water layer to a bigger water reservoir to absorb the heat. The amount of water needs to be measured exactly such that it's enough to not heat up until boiling temperature during the course of daytime, but it can also be chosen specifically such that the warmed water can be used at the end of the day and preserved in a heat insulating storing unit, and then it can be refilled with cold water the next day. Basically, a home water storage is just enough for this task. Here's some numbers just for reference. As we can see from the calculations, a small solar farm of an area of about 25 meters squared only needs a volume of water of about 6.5 meters cubed, or about 6,500 liters, which is just around the size of a home water storage, which is very attainable. The water storing layer, or the container, can be designed from Pyrex, otherwise known as borosilicate glass, such that overheat and high pressure won't cause any cracks in the layer due to the big temperature differences between day and night, to prevent the water from leaking out. Pyrex would be of great advantage to avoid any delamination and internal corrosion caused by moisture finding its way through the panel's cracks. Pyrex is known for its low thermal expansion coefficient, which makes it more resistant to thermal shocks. That's it for this presentation. Here are the references I used in this research. I hope that my design for the small solar panels water cooling system was of your interest. In case you still have any questions, you can send me an email at any of these two addresses. Thanks for watching.